the semester. Is what I typically get through in a semester's worth of calculus here. So S10 focuses on a topic called implicit differentiation. It's another differentiation strategy, just like chain rule, power rule, quotient rule, etc. It's going to open up another set of equations or functions for us to be able to differentiate. So let's practice some implicit differentiation. Our goal here for these first handful of derivatives is to find the derivative with respect to x. I just abbreviated with respect to as WRT, with respect to x. Let's try this first column. What's the derivative with respect to x? What is the derivative with respect to x? That's what this d dx notation indicates. What is the derivative with respect to x of x cubed? Don't think too hard. We've already done a million of these. 3x squared. Excellent. All right, that's pretty easy. What's the derivative with respect to x for sine x? Now, what is the derivative with respect to x for y cubed? What's different about that? It's y instead of x. So how do I take the derivative with respect to x when this isn't the same variable? What we're going to do is use chain rule. So let's think of y cubed as two separate functions. I have the cubic, the power function part, and then the inner function, the y portion. Think of that as quantity y to the third. There's the inner function y and the outer function being raised to the third power. So if I do the derivative with respect to x of y cubed, let's do the outer function first. Bring down the 3, then it's y to the second power. So that's part of it. According to chain rule, what else do I need to do? Derivative of the inner function. Well, I'm going to use notation for the derivative of the inner function as the derivative of y with respect to x. The derivative of y with respect to x is simply just dy dx. Since the variables don't match up, like Caitlin said, this is as best as I can do. What's the derivative of y with respect to x? What's the derivative of y in terms of x? That's just dy dx. Does that make sense? Let's try 5y. What would the derivative of 5y be? 5. But then what else? Derivative of 5y is 5 times the derivative of y in terms of x. 5 dy dx. Bring over the 5, because that's just a constant multiplying times my function of y. But I need to find the derivative of y with respect to x, so it's just dy dx. I'm applying this implicit differentiation using chain rule. How about sine y? There's really an inner function here. Sine is one part of this function. Y is the inner function. It's a composite. So let's do the derivative one part at a time. What's the derivative of sine? So cosine y times the derivative of the inner function. If you think of the y as the inner function, what's our notation for the derivative of y with respect to x? Yes. So here's kind of a general rule of thumb. This gets you by most of the time. If you're taking the derivative with respect to x, and it's already in terms of x, it's business as normal, right? Business as normal. If I'm trying to differentiate a term that's in terms of x, or the derivative with respect to x, don't do anything different. If I'm trying to find the derivative with respect to x, and it's got a y in it, use chain rule and place a dy dx at the very end. Think of 5y like 5x, Derivative of 5x would just be 5, but then put a dy dx on the end. Derivative of y cubed, think of it like x to the third. Then just put a dy dx on the end. All right. Let's practice finding the derivative using implicit differentiation. Let's see, how's my frame job here? All right. Find dy dx. Find the derivative of y with respect to x for this equation, x cubed minus x times y plus y squared equals 7. All right. What's the derivative of x cubed with respect to x? Okay, that's done. I'm differentiating with respect to x. So when I take the derivative of x cubed, it's just business as normal. Derivative of x cubed with respect to x should just be 3x squared. Now I need to do the derivative of x times y. Which rule would be helpful? Which rule should I follow when I take the derivative of x times y? Product. So let's subtract the product rule to help me find the derivative of x times y. So first times the derivative of the second. That's x times the derivative of y with respect to x. What notation do we use for that? dy dx. Plus the second, so I'm just going to write y. Y is the second function in the product xy. Times the derivative of x with respect to x. What would that be? 1, so I'm not going to write multiplied by 1. That's nothing. Okay, that took care of this piece. The derivative of x times y is x dy dx plus y using product rule. Next up, next term is y squared. What's the derivative of y squared with respect to x? Second, Caitlin, you said it. 2y. That's part of this because using chain rule says take the derivative of the power function first, bring down the 2y, so it's 2 times y to the first times what else? All right, do the inner function. What's being raised to the second power? That's this y portion here. What's the derivative of the inner function? What's the derivative of y in terms of x? That's dy dx. Okay, now I've also got to take the derivative of what's on the other side of the equation. What's the derivative of 7? Okay, we've differentiated. All that's left is to find dy dx. So we need to solve for the derivative. Solve for dy dx. I'm trying to find dy dx. So we need to solve this equation I just put together for dy dx. So let's see what we've got here. 3x squared minus x dy dx minus y plus 2y dy dx equals 0 when I just distribute through the negative. Look at those terms here on this part of my equation. There's 4 terms in total. 3x squared, x dy dx, y and 2y dy dx. Some of them have a dy dx and some of them do not. Let's get the ones that do separated from the ones that don't. I'm going to move the 2 terms that don't have a dy dx to the other side of my equation here on the right. I need to move this piece, so let's subtract 3x squared from either side and add y to either side. I'm basically just moving those 2 terms over to give me 2y dy dx minus x dy dx equals y minus 3x squared. By getting the terms that have a dy dx all by themselves on one side of my equation, I've forced that left side to now have a GCF, greatest common factor. What's the GCF of those two terms on the left part of my derivative? dy dx. So can I just factor out GCF? When I factor out dy dx, that's going to give me 2y minus x. Quantity 2y minus x. Dy dx times quantity 2y minus x. Equal to y minus 3x squared. One last step, solve for dy dx by doing what? Because I need to get rid of multiplying by 2y minus x, so let's just divide by that to cancel it out and have our final answer for the derivative. Here we go, final answer, dy dx, it's tough to say fast, equals y minus 3x squared divided by 2y minus x. So that's pretty much the process every single time. Take the derivative with respect to x, and then just start solving for dy dx. What you want to do to solve for dy dx, since some terms have dy dx and some terms do not, is to get the terms that do separated, removed from those that don't. So I'm going to add those that don't to the other side of my equation. And that way I have a GCF of dy dx I can factor out and solve for my final derivative with. All right, let's try one more real quick and then we'll get some practice pulled up. All right. We've done these before. It's just not been using implicit differentiation. Write an equation of the tangent line for the equation x cubed plus y cubed equals 6xy minus 1 at the coordinate 2, 3. What do I have to know first before I can write the equation of the tangent line? So I have a point on the line, I just need the slope. How do I find the slope of the tangent line? Because isn't the derivative an equation to find the slope of the graph at any point I want? To find the slope of the tangent line at any point I'm given? So let's do implicit differentiation to find the derivative of x cubed plus y cubed equals 6xy minus 1. I have to use implicit differentiation because is it really easy to solve this equation for y? We've done the derivative of like y equals equation so far. Could I solve for y on this equation pretty easily? No, y's are everywhere. I got a y cubed, I got a 6xy. These are really tough to solve for y and get an explicit function back out. When x's and y's are all mixed up, that's why we have implicit differentiation. Implicit differentiation is for when you can't get a variable by itself, when you can't get y in terms of x. Kind of like these. X to the third plus y to the third equals 6x y minus 1. All right, let's use implicit differentiation. Take the derivative of each term. This, and this with respect to x. What's the derivative of x cubed with respect to x? 3x squared, okay. What's the derivative of y cubed with respect to x? We got to use chain rule, so bring down the 3 first. 3y squared is part of it, and what else? Times dy dx. Treat the y like your inner function. Do the power function derivative first, and I multiply times the derivative of the inner, Derivative of y with respect to x is just dy dx. Okay, left half done. Equal to, now I have to differentiate 6xy and minus 1. So 6xy, that's another product rule question. Let's call 6x the first and y the second. So the first times the derivative of the second. What's the derivative of y with respect to x?
dy dx.
Plus the second, that's y, times the derivative of the first, that's just 6. What's the derivative of negative 1?
0.
Yeah, all right, so we're done with that. Okay, so let's see if we can start solving for the derivative. I need to solve for dy dx. I see 4 terms here. Let's bring down what I've got. 3x squared plus 3y squared dy dx equals 6x dy dx plus 6y.
And we subtract the 3x squared and subtract the 6x dy dx.
So you're talking about moving this dy dx term over here and moving this non-dy dx term over.
Yeah.
Okay, so you're going to put all the dy dx's on the left and all the other pieces on the right. Okay. I'll buy that. So let's move this over. 3y squared dy dx minus 6x dy dx equals, I still got the 6y over here on the right, but I've also, you said I need to subtract the 3x squared?
Yeah.
All right, sounds good. Now dy dx is a GCF that I can factor out. So dy dx times quantity, everything else, 3y squared minus 6x equals 6y minus 3x squared. Carry that through on the right. All right, here's our derivative. What do I need to do to get dy dx all alone?
Divide by 3y
Yeah,
squared.
you're just dividing by whatever's here, right? After a while, some people recognize that it's just this thing divided by these two things. They can kind of skip this factoring step out here. You recognize this as 6y minus 3x squared divided by 3y squared minus 6x. Take a shortcut. Okay, so what could I simplify that by? I just kind of caught this a second ago. Yeah, let's just divide everything by 3. Every term is a multiple of 3. 6, 3, 6, and 3 can all be divided by 3. So this would be 2y minus x squared over y squared minus 2x. There is a formula for us to find the slope of the graph at any point by plugging in the coordinate x and y. What point do I want to find the slope at? 2, 3. So plug in 2 for every x and 3 for every y. Let's evaluate dy dx for the coordinate 2, 3. So 2 times y is 2 times 3. Minus x squared, minus 2 squared. Divided by y squared, so that's going to be 3 squared. minus 2x, so 2 times 2. That's 6 minus 4, which is 2 on top. 9 minus 4, which is 5 on bottom. Slope of the graph at 2, 3 is 2/5, according to what I got by plugging the coordinate into the derivative. I know the point of tangency. I know the slope of the graph. I've got a point and a slope on my line that we can now write using point slope form. So y minus 3 equals 2/5 times x minus 2. Y minus y1 equals m times x minus x1, as point slope form would say. All right, let's see if we can solve for y. Bring down y minus 3 equal to 2/5 x minus 4/5. Add 3 to each side, so plus 3 plus 3, that's y equals 2/5 x. Let's see, 3 minus 4/5. That's 15/5 minus 4/5. When I find common denominator, that's 11/5. There we go. Yeah, some of these implicit equations look really weird when you graph them, right? I don't know enough about them to describe to you why that's the shape for that given equation. I have no idea. It's just the way it is, right? I don't know. But I do know that I've got the right tangent line, right? Yeah, sorry, those of you online here, let me share my screen with you so you can see what we're looking at. We graphed the given equation here in red. I plot the point of tangency 2, 3, and here is my tangent line we just found. Y equals 2/5 x plus 11/5. We're all just kind of staring at this graph here in red. That looks really strange. Okay, let's do this. Grab your laptops and I'll pull up some practice. U2 S10, last standard in Unit 2, before we start looking at more applications of differentiation, related rates and graph theory. All right. Looks like we got enough here to get started from the top down. We need to do second derivatives using implicit differentiation.